Hello, everyone. So today I will present some work that I have done concerning variational quantum algorithms and methods to actually execute variational quantum algorithms more statistically accurately. So since this is concerning variational quantum algorithms, let me just briefly introduce what they are. So whenever we talk about variational quantum algorithms or VQAs, we are more concerned with the following computation task, namely to minimize cost functions, let's say C. And this function is usually a function of some Hermitian observables, let's say. And such functions are classical functions. So they can be written as the trace or in general expectation values of observables like these. But if you were to do this on a classical computer, then computing expectation values of such observables will run exponentially, will scale exponentially in the number of qubits, n. So what VQAs aim to succeed is to basically make use of a hybrid system, namely a classical computer and a quantum circuit. So the quantum circuit is used to sample the expectation values. And there will be some minimization updates, iterative steps that can be performed on the classical computer. But the expectation value is not computed by the classical computer, rather it's sampled from the quantum circuits. Therefore, it makes the whole procedure more efficient for a large number of qubits, and at least this is what we hope for. And this can be immediately applied to recent era of noisy intermediate scale quantum devices or NISQ devices. Examples of VQAs are actually those that we know very well. So one such class of VQAs are quantum eigensolvers. These are eigensolvers that aim to find the minimum eigenvalue of some observable, namely some Hamiltonian, describing the dynamics of some system. Or when we talk about machine learning, then the quantum version is also a variational algorithm because it takes input data and encodes it into a quantum circuit. And the function to be minimized is actually the cost function of the input data. So these are two very popular classes of tasks, quantum information tasks, that belong to variational quantum algorithms. So very brief overview of how functions can be minimized or optimized with VQAs. So what happens is that you take either in the quantum machine learning setting, you take input data and then you encode it onto the quantum circuit. Then this comes as parameters. And what you do is that you have a set of trainable parameters that are encoded in a different set of unitaries, and you're supposed to optimize the output of this circuit that you see over here by optimizing over the circuit parameters. So you do this, and what you do is that each time you sample the quantum circuit, you arrive at a set of data, you feed the set of data to a classical computer. That classical computer will evaluate the expectation value or estimate the expectation value, and also estimate the gradient or Hessian that would then enter into the update procedure to minimize the output function. And then this classical computer will churn out a new parameter, which will be used to tune the quantum circuit for the next round of optimization, right? So this is basically the entire routine of gradient slash Hessian-based cost minimization. Now, because the functions are sampled, the gradient and Hessian components, if you use them, will also inherit sampling errors. And we need optimized sampling strategies for this, which is the main topic of this talk. So examples of gradient and Hessian-based optimization is as what you see here. So for the gradient-based methods, we know very well. These are some of the common gradient-based descent methods that we use for function optimization. And that is for gradients. Now, if you want a higher order assistance, such as Hessian components, you can then use some of these methods that are already well known in classical computation, classical optimization tasks, which we can then apply to VQAs. Now, to use these gradient and Hessian methods, we need to compute the gradient and Hessian components. And there are many ways to do that. So a very popular way that VQA community tends to favor is the parameter shift rule. The so-called parameter shift rule just basically analytically computes the gradient and Hessian components from a quantum circuit exactly, directly, right? The details don't matter, but there is also another set of techniques to compute gradient and Hessian components, which we are all very familiar with, especially in the IEEE community. So these are, for example, the finite or the generalized version of the finite difference method that computes the gradient and Hessian components approximately with some finite step size that is non-zero. And so ideally, you will need to set the step size to 0 in order to exactly compute the gradient and Hessian components. Another kind of approximate way of computing the gradient and Hessian components is to scale the parameter shift rule, thereby introducing a prefactor similar to the step size epsilon over here. But then now this prefactor will introduce also a kind of approximation error to the components computed, right? So very generally, on the left, these methods are known as analytical methods. And these analytical methods will give rise to a mean square error, which is a figure of merit that we use to compute the statistical error, or basically quantify the estimation accuracy. And this is governed by the errors due to finite copy situations, finite copy sampling. On the right, the methods here are known as numerical methods or approximated methods. And the corresponding MSE not only has the finite copy error, but also possesses the approximation error due to the inaccurate estimation of the gradient and Hessian components, right? So because of that, there is a very general consensus that numerical methods are bad, analytical methods are good, simply because there's an additional approximation error. And this approximation error would give rise to inaccurate estimation and therefore requires very small step size or very large or near unit prefactors that would inhibit the execution on these devices because you need a lot of sampling copies for that, right? So that is the general consensus. But there is a flaw, a very big flaw in these consensus. Why? Now, the comments or the remarks made here, which can be found in real published papers, by the way, this would be true if the functions are exactly computable. Then obviously we would not have the finite copy errors, and we only have the approximation errors. Then it is actually obvious to just use the analytical method, let's say the parameter shift rule, to compute the gradients and Hessians so that there will be no errors. The problem comes when you use VQAs. In this case, the functions must be sampled. All right, so the functions of a VQA circuit cannot be computed exactly. So this is the problem. And therefore, the remarks made previously no longer flies, because the mean square error would then have to be optimized over the scaling parameters, be it the epsilon parameter from the finite difference method or the lambda parameter from the scale parameter shift rule method. It has to be properly optimized over in order to minimize the overall mean square error. So the sum of the error components must be minimized, not just one of them. And such a technique is actually well known in the IEEE community. I just cited one paper, but I'm pretty sure that most of you, if not all, are familiar with such a paradigm. And when you do this, you will get a very optimal set of estimators for the gradient and Hessian estimation. And on top of that, we also average the mean square error over the trainable parameters, which is something that people have not looked at. And this average actually serves to give an average performance capacity for some given initialization strategy. Let's say for a quantum circuit, if you want to begin optimizing the output function, you would have to first initialize the circuit parameters theta here to some value and then proceed with the optimization. And the average mean square error can actually quantify the quality or the performance of such initialization strategy. Now, in particular, if we are using quantum circuits that are universal, there is this thing called the barren plateau phenomenon. So very briefly, what is barren plateau phenomenon? It is actually a phenomenon where the magnitudes or the square magnitudes of both the function and its gradient and Hessian components vanish exponentially with the number of qubits. And this phenomenon exists when you use circuits comprising two design unitary operators or Haar random unitary operators more generally. In fact, any sort of random circuit will give rise to this barren plateau phenomenon, which is which is actually an important issue to be addressed in order for VQAs to run efficiently. And we need the estimation of the gradient and Hessian components to be at least compatible with the barren plateau phenomenon, which they are if you optimize the mean square error carefully, as we will see very shortly. So just a very brief technical detail on how circuit averaging is done. In theory, you would need the assumption of two designs for circuit modules, for trainable circuit modules, in order to arrive at analytical expressions for the mean square error. The details can be found in the two papers shown below. So basically, we call this condition the two design sandwich condition. But if the condition is not met, we can still analytically treat the mean square error. But the problem is that we will not get analytical expressions. What we would get instead are bounds for the mean square error. So in this, in the slide to be followed, we will just focus on the TDS condition, but the bounds follow a very similar scaling behavior. So this basically summarizes the results of properly minimizing the mean square error in order to obtain optimal estimators for the gradient and Hessian components, right? So here we will assume that the circuits are encoded with Pauli gates. So both the input data and the trainable parameters are encoded as angles in Pauli rotation gates. So if that's the case, we are able to derive the analytical formulas for the mean square error and optimize them. And the result is as follows. The corresponding optimal estimators for both the finite difference and the generalized difference estimators, which actually exhibit slightly more complicated expressions, but here we will just look at the finite difference mean square errors, as well as the scale parameter shift mean square errors, basically the numerical errors that are properly optimized, the numerical estimators that are properly optimized, will give rise to a mean square error that scales with the dimension as well as the number of copies, not just the number of copies. So it scales as 1 over d to the power of some real values. On the other hand, the mean square error for the analytical method do not share this favorable scaling behavior. It only scales with the number of copies. So for a fixed number of copies, we see that the statistical errors don't drop with the number of qubits as compared to the optimized numerical methods. And this shows that if you properly optimize the numerical estimators, you can have estimators that are compatible with the barren plateau phenomenon. Namely, that if you really use universal circuits, then the estimators will have magnitudes that are compatible with the gradient and Hessian components, the actual gradient and Hessian components, in the presence of barren plateaus, all of which scales exponentially with the number of qubits. Whereas if you look at the gradient and Hessian components for the parameter shift rule, there's no such scaling behavior. So for a fixed number of copies, the numerical estimators are much more statistically accurate than the parameter shift estimators. So these are just graphs showing you the results of properly optimizing the gradient and Hessian components. The Hessian and gradient, the gradient and Hessian estimators, component estimators, for the two different applications of VQAs. At the top, we consider quantum supervised learning, and at the bottom, we consider quantum eigensolvers for the water molecule. And you see that for a given number of sampling copies, NT, you find that the mean square error for the parameter shift rule for the individual types of component estimation is actually larger than the optimized numerical estimators. So this is just a graphical confirmation of the results. And previously, we have been talking about optimized gradient and Hessian estimation for noiseless circuits. It turns out that we can also do this for noisy circuits. So if the circuit gates, the unitary gates of the circuit each possesses IID noise, let's say depolarizing noise, which is what I have looked at in the second work here, just recently published in 2020, this year, 2024. It turns out that we can still heuristically optimize the mean square error in order to get optimal numerical estimators, even in the presence of noise channels. However, what is interesting is that it turns out that out of the two numerical methods that I've tested, let's say the scaled parameter shift rule and the finite difference method, it turns out that the scale parameter shift rule is the method of choice, as it does not give any residual noise bias, whereas for the finite difference method, it does give some irremovable residual noise bias. And so long story short, in general, if you have noisy circuits, the heuristically optimized SPS scheme is actually the strategy to use. And so this is basically the result. The details can be found in this particular publication. So let me just conclude. So what I wanted to say, which is actually the most important message here, is that conventional wisdom that numerical methods are bad and analytical methods are good does not apply to VQAs, does not apply in general. It only applies when the function values can be computed exactly, as in the classical case. However, if you were to use quantum circuits to compute functions, quote unquote, then the functions would have to be sampled. And this wisdom doesn't apply. And so what we should really do is to minimize the averaged mean square error properly, and we can then achieve better statistical accuracies for the estimation. So these estimators are also compatible with the barren plateaus. I do not claim that the barren plateaus are removed. They still exist, and we still have to do something about it. And it turns out that for noisy circuits, the SPS scheme is actually the strategy of choice for out of all the tested numerical schemes. And with that, I thank you for your attention.